You are listening to The Vocal Technologist. Spoken Tech for your ears.
If you think AI coding tools are making devs faster, I've got awkward data.
Yeah, well, the benchmarks are, honestly, they're completely detached from what actually happens when these models hit a live, messy corporate network. The friction is just immediate.
It really is. Welcome along to Vocal Technologist. I've been incredibly keen to untangle this one. We've got a massive stack of engineering blogs and postmortems from companies like Netflix, LinkedIn, and Airbnb.
Yeah, and the mission here is to figure out why the smartest AI models on Earth, models with brain power, supposedly off the charts, are basically face-planting when they try to interact with standard enterprise databases.
Exactly. We hear heaps about the hype, but there is a hidden truth holding them back, and it's entirely about our clunky legacy plumbing.
Right, because we have to look past those sterile text-to-SQL benchmarks. In a controlled environment, sure, an AI can translate a natural language question into a perfect database query without breaking a sweat.
But real-world data warehouses are, well, they're poorly documented, full of historical quirks, and just riddled with exceptions.
Exactly. The AI agents are heavily constrained by that legacy infrastructure, not by their own reasoning capabilities.
Which means the vendors selling us these tools are basically having a lend of us if they say it's just plug and play. I was reading the breakdown of how LinkedIn had to handle this exact problem in production, and it is wild.
Oh, the container provisioning thing.
Yeah. They had to pre-provision containers and shift like 80% of their orchestration over to hard deterministic code just so their agents could think and respond in milliseconds.
That orchestration overhead is the silent killer of enterprise AI. I mean, if an agent receives a prompt, generates a brilliant step-by-step plan, but then has to spend 30 seconds waiting for a cloud container to spin up just to execute step one.
The user experience is entirely ruined. People won't wait.
No, they won't. LinkedIn realized that to get those millisecond response times, you cannot rely on the AI to dynamically figure out the infrastructure on the fly. You have to put the heavy lifting on rigid, hard-coded rails.
So the AI makes the high-level decision, but the execution path is already built and waiting.
Precisely.
Wait, I thought RAG was supposed to be the magic bullet for all this. You know, retrieval augmented generation. Doesn't that solve the context problem by just feeding the AI the right internal documents before it answers?
RGAE is fantastic for finding relevant text snippets,
Yeah.
but it falls apart when an enterprise agent needs governed structural context.
How so?
When RGAE grabs a chunk of text, it completely loses the boundaries of the source material. It strips away business meaning, data ownership, usage restrictions. The model just sees a soup of words.
Right.
It doesn't know that one paragraph is pulled from a deprecated draft policy from 3 years ago, and another is from a strictly governed, audited financial report.
So relying strictly on basic RAG is basically like handing a new employee a shredded encyclopedia and expecting them to run the company.
That is a great way to put it. They've technically got all the information in their hands.
But absolutely none of the structure required to actually make sense of it.
Exactly. A governed data product model is what replaces that shredded encyclopedia. It compiles the truth into multiple structured representations like a connected graph, a markdown wiki, or compact sidecar.
Giving it actual boundaries.
Yeah, it gives the AI repeatable operations and trusted context rather than just a loose catalog of text snippets.
Right, so here is where it gets interesting. Because if AI is choking on bad context, it means the old school discipline of data modeling, which a lot of us thought was dead, is actually more critical than ever.
Oh, it absolutely is.
I have a quiet confession. I really thought AI meant we didn't have to care about perfect data structures anymore. I figured the massive neural net would just magically sort through our messy folders and figure it out.
A lot of engineering teams made that exact same assumption. They thought raw, brute force compute power could mask messy data.
But it can't, can it?
No, clear structures and standards are how you avoid constant firefighting. A modern data team needs a flexible, mixed model approach, using the right modeling style for the specific problem. Because database schema decisions are an irreversible liability.
A dodgy database schema is like pouring wet concrete over your bad business decisions. Once it sets, you are absolutely stuck with it, and chipping it out is going to cost you a fortune.
Avoidable operational mistakes baked into that concrete are why systems like Postgres usually start failing at massive scale.
Like what kind of mistakes?
We're talking about poor indexing, blocking migrations, connection storms. You have to design schemas around actual real-world query patterns.
Which brings up a massive, highly technical change coming to Postgres 19. They're shifting their default toast compression from a system called PGLZ over to LZ4.
Yeah, that's a huge deal.
For those of us who aren't database administrators, what actually is toast?
So TOAST stands for the Oversized Attribute Storage Technique. When you have a relational database like Postgres, it expects rows to fit neatly into data pages of a specific size. But when you start dumping massive blocks of variable-length text or huge JSON-B objects into a row, it just doesn't fit. Toast is the background mechanism that automatically compresses that oversized data and slices it up so the database doesn't choke.
So it's basically Postgres trying to cram an oversized suitcase into the overhead bin.
That's pretty much it.
How does shifting to LZ4 compression actually help the AI querying it, though?
Well, the old PLD system was reliable, but quite slow. The new LZ4 implementation targets a specific 2 kilobyte threshold before it spills that oversized data out of line. It compresses data significantly faster, but its biggest superpower is that it fails fast on incompressible data.
Fails fast, meaning it just gives up.
Yeah, imagine trying to compress a bowling ball. You could spend hours trying to squeeze it down, but it's physically impossible. The old system would waste precious CPU cycles attempting to compress data that simply couldn't be shrunk.
Oh, what?
LZ4 recognizes almost instantly when a block of data is incompressible. It stops trying, saves the CPU cycles, and just moves on. It's a foundational plumbing fix that frees up immense compute power for everything above it, including your AI agents.
If that solves the live querying problem, what happens when the AI needs to analyze historical changes? Because I was reading about backfilling, and apparently it is the most underrated data pipeline feature going around right now, especially when paired with bitemporal writes.
Bitemporal writes are fascinating.
I'll admit, my temporal writes sounds like something out of a time travel movie.
It does, but it's surprisingly simple in practice. Bitemporal writes mean your database tracks two distinct timelines. The first is the valid time, which is when a fact was true in the real world. The second is the system time, which is when that fact was actually recorded in the database.
Give me a real-world example of that.
Okay, say an employee gets a promotion and a pay rise on Monday, but HR doesn't actually enter it into the system until Thursday.
Standard corporate lag.
Exactly. If your AI is analyzing payroll trends on Wednesday and it only looks at a single timeline, it's going to get confused. Bitemporal writes allow the system to safely wipe and reload historical data without corrupting the current state.
Giving it a clean version of events.
Yeah, it gives the AI a perfectly consistent, mathematically accurate view of history to learn from.
Just quickly, if you're keen on poking around the guts of tech like this with us, make sure you hit subscribe. We love getting past the noise and into how this stuff actually works. So if a central database like Postgres is such a bottleneck for hundreds of AI agents trying to think at once, what if we just blew the database apart? What if we gave a piece to everyone?
This is a major architectural shift being called to every agent its own database. Instead of hundreds of agents fighting for bandwidth to query a massive central monolith, you give every single agent its own local DuckDB instance.
DuckDB is popping up everywhere right now. It's designed for analytical queries, but why is it so incredibly fast for AI to use locally?
It comes down to a concept called vectorized execution. Traditional databases process data row by row. It looks at row 1, processes it, then moves to row 2. DuckDB processes data in cache-friendly batches of 2,048 rows at a time.
I always love the hyper-specific numbers in tech. Why exactly 2048?
Because it fits perfectly into the physical CPU cache. When a computer processes data, pulling information from the main RAM takes time. The CPU cache is a tiny lightning-fast memory bank located directly on the processor itself. By grouping exactly 2,048 rows, DuckDB ensures the data sits right where the processor needs it.
That makes a lot of sense.
It drastically reduces copying, minimizes the overhead of function calls, and makes parallel execution incredibly efficient.
Imagine carrying groceries inside from the car. A traditional database carries one apple at a time. Vectorized execution is like putting 2,048 apples into a perfectly sized basket and carrying them all at once. The CPU cache is the basket.
That's a spot-on way to look at it.
But hang on, I see a massive flaw here. If you give every single agent its own local database, aren't you just creating a million disconnected, dodgy silos across the company? Like, Agent A could be looking at yesterday's data while Agent B is looking at today's.
And that cache coherence problem is the immediate risk, yeah. To solve it, the agents do not exchange mutable snapshots of data. They don't send files back and forth. Instead, they exchange immutable pinned objects called slice refs.
What actually is a slicer ref?
Think of it as a cryptographic receipt. A slicer ref contains a snapshot ID and a content digest. It proves exactly what state of the data the agent is looking at.
So they can check each other's work.
Right. Before any downstream computation runs, a comparison layer checks these receipts. It verifies if the agents are looking at identical information or if there's been a breaking change.
So they have their own independent brains, they can compute at lightning speed locally, but they are all reading from the exact same sheet of music, and it's cryptographically verified. That solves the local agent problem. But enterprise data still requires massive distributed processing. I mean, you can't fit a petabyte of corporate data into a local DuckDB instance. The heavy lifters are having to adapt to AI, too.
The big rigs of data engineering are evolving incredibly fast to keep up. Apache Spark 4.2 has landed, bringing native geospatial types and change data capture queries.
Okay.
But the most fascinating shift in the big data space right now is the integration of Rust.
Everyone loves rewriting things in Rust at the moment. It's almost a meme. But is it actually worth the massive headache and learning curve for enterprise data teams?
Well, if you look at the cloud computing bills for these massive companies, the performance gains suggested is absolutely worth it. Look at Apache Data Fusion Comet. Spark is traditionally built on Java. Comet keeps Java for the query planning, so Java is still the brain, but it uses Rust for the native arrow execution, making Rust the muscle.
And what does that actually do to the performance?
It dramatically speeds up how Spark reads massive data structures, like iceberg tables. In a 3 terabyte benchmark test, Comet accelerated 102 out of 103 queries and slashed the total runtime by about 40%.
Wow. If you're sitting there wondering why your company's cloud bill is astronomical, this is why it matters to you. A 40% reduction in compute time at an enterprise scale isn't just a fun technical metric. That is millions of dollars saved overnight. How is Rust achieving that much of a speed up?
Beyond Rust's inherent memory safety and speed, Data Fusion now automatically exploits something called exact and partial sortedness.
Break that down for me.
So if the query engine knows the data is already sorted, even partially, it uses Parquet min-max statistics. Basically, every block of data has a tiny label saying the lowest number in here is X and the highest is Y.
Okay, I follow.
If you are querying for a date in August and the block's label says it only contains data from January to March, the engine doesn't even open it.
It just skips it entirely.
Yes, it uses dynamic filters to avoid full table scans entirely. It skips blocking sorts.
Yeah.
It's just a vastly smarter execution.
Which brings us to the part nobody is really talking about out loud. Once the plumbing is fast enough and the data is moving efficiently, how do companies actually run, serve, and evaluate these massive LLMs in production without going completely broke? Serving an LLM to millions of users is a totally different beast than running a prototype locally on your laptop.
Netflix is a prime example of doing this right. They run their LLM, serving entirely in-house using a JVM-based platform with vLLM as the underlying engine. But the technical choice that really stands out is their use of patched guided decoding.
I loved reading about this. They basically alter the generation process to completely prevent the models from spitting out malformed JSON. Why is that so crucial?
Because JSON is the language that different parts of a software application use to talk to each other. If an AI generates a response and it misses a single bracket or a comma in that JSON code, it can completely crash the downstream application.
Just from one comma.
Oh, absolutely. The user gets a blank screen, the system fails, and it requires manual intervention. Guided decoding restricts the model's vocabulary at every single step of generating an answer, forcing it to only output mathematically valid syntax.
It is basically putting bowling bumpers on an LLM, so it literally cannot throw a gutter ball into your app's front end. It forces it to hit the pins every time.
And while Netflix solved the serving stability side, Airbnb tackled the evaluation bottleneck. Evaluating whether a new AI model is actually better than the old one used to take them weeks. They managed to cut their evaluation cycles down to under a single day.
How do you shave weeks off an evaluation cycle?
By heavily caching generated references and judge scores. They analyzed their testing and realized that over half of the model outputs across different candidates were identical strings. The models were giving the exact same answers to certain prompts.
So they were just double testing the same thing.
Exactly. So instead of wasting expensive compute power reevaluating the same answers, they just pull the previous score from the cache.
That is brilliant. And they combine that caching with training small LaRA adapters to fix bugs in the models. The documentation mentioned they were using a rank under 50 to train these adapters in under an hour on a single GPU. Can you give me the plain English explanation of what a LoRa adapter is and why a rank under 50 matters?
Sure. Training a massive AI model from scratch takes weeks because you're tweaking billions of internal connections. LoRa adapters are like placing a thin, transparent layer of sticky notes over the AI's brain.
Okay.
Instead of rewiring the whole brain, you only write on the sticky notes. The rank refers to how many sticky notes you're using. Because a rank under 50 means very few sticky notes, Airbnb can train that tiny layer in under an hour. They can literally push same-day fixes to their production models.
It's agile software development, but applied to AI neural weights. But Meta is taking this even further with a system called Trellis, which uses what they call experience graphs. Honestly, it sounds like science fiction.
An experience graph stores a persistent history of everything the agent has ever tried. It logs the artifacts, the rewards, the search data, and the causal history. It maps out exactly what succeeded and what failed in previous tasks.
The data Meta published showed that by reusing that past experience, the agents matched top performance 10 times faster, and it cut the token cost for successful solutions by 52%. Half the cost, 10 times the speed. But there has to be a catch.
There is a catch. If you force the agent to reuse memory too aggressively, it severely reduces its exploration capabilities. It starts relying entirely on old habits and known paths instead of looking for better, novel solutions.
It gets lazy. Just like a human relying on a template instead of writing something fresh.
You have to perfectly balance exploiting past knowledge with exploring new paths. To close the loop on training, we are now seeing teams use OpenTelemetry traces, or OTel, to convert live production feedback into training labels.
So taking the telemetry from how real users are interacting with the app in the wild and feeding that back to train small, local coding models around the 7 to 13 billion parameter mark.
Right. And by fine-tuning on actual company-specific production traces, these small, secure local models are hitting roughly 80 to 85% of our frontier model quality.
You don't need a trillion parameter giant model if your small, cheap model is trained perfectly on your specific corporate data. Pulling this all together, it feels like the companies actually winning the AI race aren't the ones just swiping a credit card to buy better, bigger models. They're the ones painstakingly fixing their data plumbing.
The broader market is validating this entirely too. Look at Dremio selling to SAP. It is definitive proof that a lakehouse-only model will not survive AI's demands for fresh, unpredictable, real-time querying. You need broad reach across all your infrastructure.
And you look at Databricks hitting a $188 billion valuation. It proves that the line between a data platform and an enterprise AI provider has completely vanished. They're the exact same thing now. If your data platform can't serve AI efficiently, it's obsolete. Think about your own company's data infrastructure right now. If you gave an AI agent full access to it tomorrow, would it become an absolute genius, or would it just confidently automate your organizational chaos? Hope that helps you sort the good from the dodgy vocal technologists. See you soon.
Spoken Tech for your ears.